Hello everyone, here is Davide Pinzan. Today I'd like to present this recent IEEE transaction on power delivery publication titled Performance of Composite Outdoor Insulator under Superimposed Direct and Switching Impulse Voltages. On the left-hand side of the slide, it's possible to see the outdoor insulator which was tested at the facility of Universidade do Porto. And on the right-hand side, in green, the voltage superimposition wave shape which was applied. This is the result of the secondment which I carried out in Porto, and it's a collaboration between Cardiff University and Porto University. First, the pole-to-ground fault will be explained. The rain conductivity range chosen for the test will be shown. Then the test circuit, EMTP-ATP transient results, the COMSOL geometry and COMSOL results, the test results, and the influence of direct voltage on the flashover voltage. Similar trends at higher voltages from other authors, conclusions, and future work. In an HVDC bipolar scheme, a positive and a negative poles are present. When one of the two poles experiences a fault to ground, the result on the healthy pole is the superimposition of a transient voltage on the operational direct voltage. This transient overvoltage is similar to a switching impulse. This is shown by the three reference studies by IEEE transactions. With regards to rain conductivity range, this map shows that the rain is acid, particularly in the industrialized areas of the world. In particular, a Japanese study shows that in Japan, the resistivity of rainwater is particularly low in some areas, and this chart shows its frequency. The Japanese study has inspired the choice of resistivity, rain resistivity, for our study. Therefore, the lower end of the resistivity has been chosen, starting from a value of 10.4 kiloohm times centimeter and going below that value to study the most critical condition for the insulator. On the upper figures, we can see what were the past configurations for this type of test. And on the bottom, the one which was used for this study. In common, they have the following items. First of all, a DC supply, then a Marx generator for the generation of the switching impulse, a sphere gap to insulate the two sides of the circuit, and the test object, in this case, the insulator. An EMTP-ATP simulation was needed in order to see what was the actual voltage applied on the insulator. In fact, in the laboratory, it was possible to measure only a transient voltage, shown on the right-hand side of the slide. On the left-hand side, instead, the green simulated voltage wave shape can be seen, and in particular, it can be acknowledged that a high voltage derivative in time was applied to the insulator due to the breakdown of the sphere gap. This would cause an enhanced risk of puncture on the insulator. The COMSOL geometry is the following, and it highlights that the test was performed vertically and horizontally for a medium voltage insulator rated for 16 kilovolts. The COMSOL results, in particular the equipotential lines, can justify why the test results for the dry clean condition, were favorable for the horizontal orientation. In fact, the equipotential lines close to the ground electrode of the vertical configuration are more squeezed with regards to the horizontal one. In other terms, as this chart shows, the electric field close to the ground electrode of the insulator is higher in the vertical case with respect to the horizontal. These are the main test results. On the left, the switching impulse only, and on the right, the superimposition of the switching impulse on the negative direct voltage. First, for the dry case, for both figures on the left, we can see that the horizontal configuration has performed better, and this was justified by the results from COMSOL. Also, the same trend can be observed for the rain cases. For the rain cases, the horizontal configuration is performing better than the vertical. Moreover, as the conductivity of the medium increases, the performance of the insulator decreases. The flashover voltages decrease. To check what's the difference in between the switching impulse only performance and the superimposition performance, this chart was computed. It's possible to see that in the majority of cases, the superimposition has a negative influence on the performance of insulator. And this is particularly clear for the two dry cases and the first wet case. Similar trends can be observed from past studies. In particular, this one from Cortina shows that when the insulator is wet, its flashover voltage is lower than when it's dry. Moreover, the superimposition of direct voltage and switching impulse decreases the performance with respect to the switching impulse only. Similarly, Watanabe, for two different profiles of insulators, show similar trends. The switching impulse only has flashover voltages which are higher than the superimposition. So these observations are done at higher voltages and confirm the observations done by our study. In conclusion, a test method is provided, which is not provided by standard test methods. In most cases, the superimposition is more severe than the switching impulse only case. However, the disturbance which the insulator is able to withstand in the laboratory is much higher than the ones that should be seen in the field. The conductivity range seems sufficient to be studied up to 150 microsiemens per centimeter because later, after this value, the results saturate. The flashover voltage tends to saturate. With regards to future work, there is a need to study under pollution conditions, and it's very important, especially in a dry condition, to use the same electrodes as in the field because they very much determine the performance of the insulators. Thank you very much. Any questions?